If heteroscedasticity is found, the estimators are no longer efficient, and the remedial measures for this will depend whether the sigma I squared is known or sigma I squared is not known. So when sigma I squared is known, we use the method of weighted or generalized least square. So what is a WLS or GLS, and how does it differ from OLS? To understand between WLS and OLS, let's look back to this figure. This straight line is the SRF, giving the estimated Y. A, A, B, C are the data points. So we can see the distance between the actual data and SRF differs. Some points are near to the line and some points are not. For example, point A is closer to SRF compared to point C. So we can see the distance between the data and the line, which is the UI hat, varies. The OLS method minimizes the sum of squares errors, where equal weights or equal importance is given to all observations. Observations with large variance are less. We know that observation with a large variance are less informative than observations with small variance, and therefore should be given less weight or importance. From the figure, point C therefore should be given less weight or less importance than other values. Point C is farther from the line compared to others. OLS unable to use this information, but WLS or GLS can. In WLS or GLS, point C will relatively get smaller weights than the other 2 points. Why? Because observations from population with greater variability should be given less weight or less importance than those from population with smaller variability. To understand further, let's look back to the regression model. We have y regress on x. So to see clearly, we will put x naught next to beta 1. So we have here I1 beta 1 x naught I plus beta 2 xi plus ui, whereby this x naught I is just simply equals to 1. So here assume variance sigma I squared are known. So what we need to do is, from the previous equation, we need to divide each of the term with sigma I. So we have yi divided by sigma I, the x naught I divided by sigma I, xi divided by sigma I, and ui divided by sigma I. So all these, we write it as yi star. So yi star is denoting yi over sigma I. X naught I star is denoting this in bracket, and then xi star is denoting this one, which is xi over sigma I, and so on. So in GLS or WLS, what we are doing is actually we are regressing the new yi or yi star, okay, on x naught I star and xi star. When we use the new regression model, which is the y star and xi star, the variance of the ui star, if you look back into the formula, is expected value of ui star squared, and this ui star is ui over sigma I, and this is 1 over sigma I squared, expected value of ui squared. So this one we bring it out from the expected value, and expected value of ui squared is sigma I squared by the definition, okay, since we have heteroscedasticity. But then this denominator we can cancel out with sigma I squared, and therefore we get the variance of ui star is 1. So previously our variance of UI is hetero, okay, but then now our variance of UI star is 1, which is constant. So from heteroscedasticity we get an homoscedastic variance, so meaning that the procedure of WLS or GLS transform the model from estimators that is not blue. Now you are producing estimators are blue. Example 11.7 is the illustration of the method of weighted least square. So here we have a variable y, which is the compensation, and also x is the employment size. So we know that this is the variable x that is related to heteroscedasticity, meaning that as employment size increases, we can see that the variance of the compensation also increase. And this is the sigma I, which is known. So what we need to do is we need to divide y and also x with sigma I. So we have this yi over sigma I, new column, and also xi over sigma I, another new column. So this is actually the y star and also the x star. So the new regression model will be the y star on x star, and when the intercept is divided by sigma I, so we have this in the bracket 1 over sigma I, so we need to also regress actually this y star on 1 over sigma I and also x star. So this is the estimation output when we regress y star on I over sigma I and also x star. So you see the new regression model does not have any intercept. It is a regression through origin. So we can set this up in the e-views by not having any constants in the syntax or in the command. So this is the result when we are doing WLS, and this is the result when we are doing the OLS. So here we are doing the remedial measures for heteroscedasticity for when sigma I is known. So here our estimators is blue, but here our estimators is not blue. Since t-tests and f-tests are no longer valid, or t-stats or f-stats are not reliable, we need to go into the wide heteroscedasticity, consistent variance and standard errors, meaning we need to get the robust standard errors. So from e-views, what we can do is once we estimate the equation, okay, this is y, c and x, and then we can go for the option menu here, and then we can click Huber-White coefficient covariance. So choosing that option, the first part is the usual OLS, whereby we have the problem of hetero, and then when we do the robust standard error, we have a new standard error, but the coefficient is just the same, the R squared is the same, only that the standard error is different. So this one is the robust standard error, and this t-stats is now reliable and valid. And then if we see the p-value, both of the estimators are significant. So here, when sigma I squared is not known, as before, we can get the robust standard error. So once you find the problem of hetero, you can always report the original OLS standard error, and also write the wide standard error or the robust standard error, and just using the t-stats that is reliable.